Okay, so let's get a jump start on our lesson tomorrow and start talking about improper integrals. So I want to look at the following integral and try to define what's wrong with what I'm showing you below here. Okay, let me emphasize, before we even go there is something wrong with that. It's not right, okay? So let's go through this evaluation. I've already got it pre-written. And so I'm going to do the integral from -1 to 1 of dx over x squared. Of course, how do you do the integral of 1 over x squared? Well, generally we write it as x to the -2, and then we find the antiderivative using the power rule. -2 plus 1 is -1. Divide by -1, that's just negating it. So thinking I'm using the fundamental theorem of calculus, I'm going to put this there in invisible ink. That means I can evaluate this definite integral by finding the antiderivative and evaluating it at the two endpoints. So I plug in 1 and I get -1. I plug in -1, I get 1. So -1 minus 1 is going to be -2. Okay, seems perfectly reasonable, right? So let's go a little bit further. This is the graph of y equal 1 over x squared. That's the thing we're integrating, right? Do you guys see what's wrong with it yet? Well, look at what's happening here. What is happening right at the y-axis? Ta-da! The integrand's not defined at x equals 0. It's not even defined there. 1 over x squared is not even defined at x equals 0. So what does that mean? Well, more to the point, it's not continuous there. There is a discontinuity at x equals 0. If it's not defined, it's definitely not continuous. And let me remind you of what the fundamental theorem of calculus says. It says that if f is continuous on the interval, let me just point that out. If f is continuous on the interval a, b, and f of x is an antiderivative, then the integral from a to b of f of x dx is equal to f of b minus f of a. That's an if-then. That if f is continuous is really, really important there. If f is continuous. So, well, we do have ways of dealing with things when it's not continuous. And how do we do that? Well, that's what improper integrals are about. So let's just look at, I'm going to go a little bit backward from the book because I started with this example. I'm going to look at what the book is calling type 2 improper integrals. And that's going to be the integrals from a to b of f of x dx where there's a discontinuity. On the closed interval AB. So there being a discontinuity tells us what? Well, let's look at it first way. F is discontinuous at A. Let's suppose F is discontinuous at A. So for example, I could look at the integral from 0 to 1 of dx over x squared. X squared, 1 over x squared, the integrand is not continuous at 0, right? Well, how are we going to work that? Well, we're going to write it as a limit. It's continuous from b to 1, where b is bigger than 0. And so we can take this as the limit as b goes to 0 from the positive side of this integral. Now, this is assuming, of course, f is continuous on the half-open integral. Open at a and closed at b. And so if we do this, well, using the fundamental theorem of calculus, since it's continuous on the interval from well, of course, I've changed my names from B to A, so this is continuous on this interval because B is bigger than 0, from B to 1. This is going to be the limit as B goes to 0 of, well, evaluating that, that's going to be negative x to the negative 1. Evaluate it from B to 1, which is limit, of course this is going to 0 from the positive side, B goes to 0 from the positive side, of minus 1 minus 1 over B, so that's plus 1 over B. So what happens is B goes to 0. Can you somebody tell me here? As B goes to 0 from the positive side, 1 over B goes to infinity, 1 over B minus 1 goes to infinity, this goes to infinity. Since we got an answer that was infinity for that limit, we say it diverges, the integral diverges. If we had a finite answer, it would converge. So what is the general situation here? The general situation, if f is continuous on the open interval from A to B and discontinuous at x equals A, then the integral from A to B, f of x dx, is defined to be the limit as t goes to A from the positive side of the integral from t to B, f of x dx, if that converges, if that limit is finite. Otherwise, we say it converges, diverges. Okay, so that is key here. So let's circle that in red. So if it's continuous at every point except for the left endpoint, we can evaluate the integral as a limit as you go towards that left endpoint. If that limit is finite, then that's what that integral is going to be. If the limit is infinite or doesn't exist, we say it diverges. Okay, so now, what do we do? What are the other type 1 integrals? Well, let's suppose f is continuous on the half open interval from A to B, not including B, and discontinuous. At B. Well, this is exactly the same thing. What are we going to do? We're going to define the integral from A to B is going to be defined of this little f as the limit as t goes to B from the left-hand side this time of the integral from A to t f of x dx if that limit is finite. Is finite. Otherwise, we say it diverges. And then finally, what is the third? That's exactly the same situation as above, right? It's just the other endpoint. And the last situation is, well, suppose, let's do a different color here. Suppose f is discontinuous at some point C between A and B. And so let's go back to that first example. The first example we looked at up here, this is that situation, right? It's discontinuous at 0, which is between -1 and 1. In that case, if both the integral from A to C of f of x dx and the integral from C to B of f of x dx converge, that is, they don't diverge, then we define the integral from A to B of f of x dx to be the sum of those, right? Just like we would do the sum of integrals in general. That would be the sum of the integral from A to C of f of x dx plus the integral from C to B of f of x dx. If either one of those does not diverge, if either one converges, if either one diverges, then the integral from A to B of f of x, we say that diverges as well. Okay, let's